Have you ever felt like the universe is holding secrets? Like there are rules governing reality that just defy common sense? For centuries, we've explored the world around us, from the macroscopic wonders of galaxies down to the microscopic building blocks of matter. And the deeper we've looked, the stranger things have gotten. At the very foundation of our modern understanding of the cosmos lies quantum mechanics. It's the physics of the tiny, the realm where particles behave in ways that make our everyday experiences seem utterly mundane. It's the physics that tells us a particle can be in two places at once, or that measuring something changes its very nature. It's beautiful, it's powerful, and let's be honest, it's downright weird. The legendary physicist Richard Feynman, a man who wrestled with these ideas his entire life, famously said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." And for a long time that felt true for many, myself included. It felt like this abstract philosophical realm of paradoxes, confined to lecture halls and thought experiments. But here's the astonishing paradox. Today, right now, we are building cutting-edge technologies, not just based on quantum mechanics, but technologies that actively control and harness this fundamental weirdness. Atomic clocks that keep time with unbelievable precision, quantum sensors that detect the faintest signals, and yes, quantum computers that promise to solve problems currently impossible. So what if we could defy Feynman's playful warning? What if we could peek behind the curtain of quantum weirdness and see how it's being transformed from a mind-bending concept into something profoundly practical? That's what we're going to do today. We're going to embark on a journey through three key examples of quantum systems. Think of them as layers, each one peeling back a bit more of the mystery, bringing us closer to understanding the incredible potential of quantum computing. We'll see how these systems, whether it's a lone electron, a single atom, or a custom-built electrical circuit, can be coaxed and controlled to behave in these strange, quantum ways. And by the end, I hope you'll see that the weirdness isn't just a quirk. It's the very source of their power. We often picture electrons as tiny little balls orbiting an atom, but at the quantum level, things are far more abstract. Associated with these fundamental particles is a quantity known as spin. Now, the name spin is a little misleading. It's not exactly like a miniature planet spinning on its axis. It's a fundamental property, like mass or charge, but the name comes from the fact that it behaves analogously to angular momentum. It's as if it has an intrinsic internal rotation. And here's where that analogy helps. Just like a spinning charged object creates a magnetic field, the spin of an electron effectively makes it a tiny little magnet. Imagine an electron as a miniature bar magnet with a north pole and a south pole. Crucially, when we measure the spin of an electron, we find that its magnetic alignment can only point in one of two opposite directions relative to an applied magnetic field. We call these spin up and spin down. Think of aligning that tiny bar magnet either pointing perfectly upwards or perfectly downwards along a specific axis. So at first glance, the electron's spin seems pretty straightforward, right? It's binary, up or down. If this were a classical system, a system we studied using the physics of our everyday world, that would be the complete story. We could have an electron with its spin pointing up, or an electron with its spin pointing down. End of discussion. But this is where quantum mechanics steps in and says, hold my probability amplitude. This is where things get interesting, and, for some, a little mind-bending. In quantum mechanics, the possible states a particle can be in are determined by solving a fundamental equation called the Schrödinger equation. The solutions to this equation give us a set of allowed states, often called eigenstates. For the electron's spin along a given axis, the eigenstates are exactly what we just talked about: spin up and spin down. These are the definite states it can be in if you measure it. But here's the quantum leap. The electron isn't limited to only being definitely spin up or definitely spin down before you measure it. Quantum mechanics allows for something called superposition. This means the electron can exist in a combination, a kind of simultaneous blend, of both spin-up and spin-down states at the same time. It's not half and half in the classical sense. It's more like having the potential to be either until the act of observation forces it to commit. Imagine a ghost that could potentially appear in two different locations, but as soon as you shine a light on it, it materializes in only one of those locations. The superposition is the state before the light is shown. This ability to be in a superposition of two states, like spin up and spin down, is one of the defining characteristics of a quantum bit, or qubit. Think about a classical analogy, a light switch. It can be on or off. That's binary. Just two definite states. A qubit, like our electron's spin, can be on, spin up, off, spin down, or it can be in a superposition of on and off simultaneously. Now you might think, wait, a door can be open, closed, or partially open. Isn't that like superposition? This is a great question, and it highlights the crucial difference between classical intermediate states and quantum superposition. Yes, a door can be in a state somewhere between fully open and fully closed. But here's the difference. When you look at a partially open door, when you measure its state, you see that it is, say, 45 degrees open. Its state is definite and observable in that intermediate form. It doesn't suddenly snap to being fully open or fully closed just because you looked at it. In stark contrast, if our electron is in a superposition of spin up and spin down, and you measure its spin, you will never measure it to be in that combined state. Instead, the act of measurement collapses the superposition. You will measure it as either definitively spin up or definitively spin down. The outcome is probabilistic, determined by how much of each state was in the superposition. But the result of the measurement is always one of the definite classical outcomes. This measurement collapse is one of the most counterintuitive and debated aspects of quantum mechanics, but it's fundamental to how quantum systems behave and how quantum computers work. The superposition allows for a richer state space before measurement, and the collapse is what gives us a concrete result. To help visualize this strange superposition state for any two-level quantum system, like our electron spin, physicists use something called the Bloch sphere. It's a brilliant piece of mathematical geometry that packs a lot of quantum information into a simple 3D image. Imagine a sphere. The surface of this sphere represents all the possible superposition states of our two-level system. One pole, let's say the North Pole, represents one of our definite states, spin up, or traditionally called 0. The opposite pole, the South Pole, represents the other definite state, spin down, or 1. Any point on the surface of this sphere that isn't at the exact poles represents a superposition state. The further away from the poles you are, the more balanced the superposition is between the two states. There are two important angles on the Bloch sphere that define any given superposition state. Theta, theta. This is the angle measured from the z-axis, the axis connecting the spin-up and spin-down poles. This angle tells us the proportion or amplitude of the spin-up and spin-down states in the superposition. It directly relates to the probability of measuring either spin-up or spin-down when the superposition collapses. If theta is 0 degrees, the North Pole, the state is 100% spin-up. If theta is 180 degrees, the South Pole, the state is 100% spin-down. If theta is 90 degrees, halfway between the poles forming the equator, the state is an even superposition, meaning there's a 50-50 chance of measuring spin-up or spin-down. Phi, FF. This is the second angle, measured around the equator, the azimuthal angle. This angle represents something called the phase of the superposition. While it doesn't change the probability of measuring spin-up or spin-down for a single qubit, it is absolutely crucial when you start combining multiple qubits. This phase allows for the quantum phenomena of interference, which is a key ingredient in many quantum algorithms, enabling quantum computers to outperform classical ones. We'll talk more about phase and interference in a future video, but just know that this angle on the Bloch sphere represents a real, controllable aspect of the quantum state. So, the Bloch sphere gives us a beautiful way to map and understand the state of a single qubit, capturing both its potential outcomes, through theta, and its capacity to interfere, through phi. It shows us that a qubit is far more than just an on-off switch. It's a point on a sphere, with infinite possible states before measurement. Okay, that's our first layer, the weirdness of superposition and the visualization tool of the Bloch sphere. Now let's peel back another layer by looking at a slightly more complex, but very common, quantum system, the atom. If we zoom in on something like a single hydrogen atom, the simplest atom, with just one proton and one electron, we find more of these discrete quantized states, but in a different flavor than spin. In the case of the electron spin, we were looking at its intrinsic angular momentum. In the hydrogen atom, we often focus on the orbital states of the electron, the energy levels the electron can occupy as it whizzes around the nucleus. When we solve the Schrödinger equation for an atom, instead of typically getting just two allowed states like spin up, down, we get a whole set of distinct energy levels. These are often labeled by an integer, n, starting from n(1) for the lowest energy, ground state, then n2, n3, and so on, forming an infinite tower of possible energy states. Here's where the control comes in. If an atom is in one of these energy states, say n tau to 2, we can cause the electron to transition to a higher energy state, say n phi 5, by interacting with it using light, specifically a laser. The key is that the energy difference between any two allowed states, like n22 and n25, is fixed and discrete. Light comes in packets of energy called photons, and the energy of a photon is directly related to the color or frequency of the light. So if we shine a laser on the atom with a color, frequency, that precisely matches the energy difference between the ny2 and n5 states, the electron in the atom can absorb a photon from that laser beam and jump up to the higher energy ny5 state. It's like hitting a specific tuning fork. Only the right frequency will resonate and cause a change. For example, in hydrogen, shining a red laser might correspond to the energy needed to go from the n.2 to the n3 level. A bluer, higher energy laser might correspond to the n2 to n5 transition. By choosing the color of our laser, we choose which specific transition we are targeting. We can also do the reverse. If the electron is in a higher state, like n5, shining a laser of the correct color can stimulate it to emit a photon and drop back down to a lower state, like n2. This process is called stimulated emission. Now, while an atom has many energy levels, for the purpose of building a qubit, we can focus on just two specific levels, say n22 and n5. We treat these two levels as our effective qubit states. n22 becomes our 0 state, and n5 becomes our 1 state. We can mostly ignore the other levels by making sure our control signals, lasers, only have the specific frequency that couples these two levels. Just like with the electron spin, our atom can be in the n2 state, 0, 1, the n5 state, Ja 1, or a superposition of both. And we can represent this on our Bloch sphere, where the North Pole is now the n2 state, and the South Pole is the n5 state. How do we create such a superposition in an atom using our laser? This is where the duration of the laser pulse becomes critical. If we shine the laser with the correct frequency for a specific amount of time, we can cause the electron to transition completely from n-2 to n5. This duration of time is called a pi pulse, p-pulse, because on the Bloch sphere, It corresponds to rotating the state vector by 180 degrees, p radians, moving it from the North Pole to the South Pole, or vice versa. It flips the qubit state. But what if we only shine the laser for half that time? A pi2 pulse, p2 pulse. This pulse, still at the same correct frequency, only rotates the state vector by 90 degrees, p2 radians. Starting from the North Pole, ENV2, a p2 pulse moves the state halfway down to the equator. As we saw earlier, a state on the equator of the Bloch sphere represents an even superposition. In this case, an equal blend of the N2 and N5 states. This ability to use precisely timed pulses of energy, like laser light, to move a quantum system between its definite states and into superpositions is a fundamental technique in building and controlling qubits. It's like having a precise dial for controlling the probability of measuring one state or the other, and that vital phase angle. Add practical connection, analysis, and think about the practical connection here. Atomic clocks. These are the most accurate timekeepers ever built. They work by using lasers to probe the exact stable energy level transitions in atoms like cesium or rubidium. The frequency of the laser light needed to make these transitions happen acts as an incredibly precise, natural pendulum. We use these controlled quantum jumps to define our units of time. So the same fundamental principles of discrete energy levels and controlled transitions that allow us to create atomic qubits are already powering our most precise technology. This isn't just theory, it's engineered reality, so we have superpositions in a single system, controlled by external pulses. What happens when we bring two quantum systems together? This is where the third layer of weirdness, and arguably the most powerful, comes in. Entanglement. Imagine we have two of our atomic qubits, atom A and atom B. Let's say we prepare each of them individually. We apply a p2 pulse to atom A, putting it into an equal superposition of its 0 and Y1 states, let's say N2 and N5 again, relabeling to 0 and 1 for simplicity. We do the same for atom B. If these two atoms don't interact with each other, the state of the combined system is just the product of their individual states. If A is in 0 plus 1, Chi2, and B is in 0 plus 1, mod 2, where the 2 is for normalization, don't worry about that detail for now, the total state is a superposition of all four possible combinations: 100, UI1, 10, and 11. Each of these four possibilities would have an equal probability, 25%, of being measured if we measured both atoms. In this case, if we measure atom A and find it to be non-zero, what does that tell us about atom B? Absolutely nothing. Atom B is still in its own superposition, and we have a 50-50 chance of measuring it as 0 or B1, regardless of what we found for A. The two systems are independent, even though each is in a superposition. Now let's consider a different kind of combined state, one that is not just the product of individual superpositions. This is where entanglement lives. Let's look at a famous example called a Bell state. One of the Bell states is a superposition of only two possibilities: the state where both atoms are 0, Schwar Osrers, and the state where both atoms are 1, Schwar 11. The combined state looks like Osrers plus 11, 2. Notice that the other two possibilities, Yasi1 and 10, are completely absent from this superposition. Here's the magic of this state. If we prepare atom A and atom B in this entangled Bell state, and then we measure atom A, the outcome has profound implications for atom B. If we measure atom A and find it to be in the 0 state, because the total state was a superposition of only indrars and 11. Finding A as 0 means the system must have collapsed to the Osrers part of the superposition. And if the total state is Osrers, then atom B must also be in the zero state. We know this instantly without ever touching or measuring atom B. Similarly, if we measure atom A and find it to be in the 1 state, the system must have collapsed to the 11 part of the superposition. This means atom B must also be in the 1 state. Again, we know this about B the moment we measure A. This is entanglement. The states of the two particles are so deeply linked, so correlated, that measuring one instantly tells you the state of the other, no matter how far apart they are. Einstein famously called this spooky action at a distance because it seemed to imply information was traveling faster than light, although modern understanding shows it doesn't violate relativity in a way that allows for faster-than-light communication. Think about the classical glove analogy again. If you find a left-handed glove, you know its entangled partner, the right-handed glove, is out there somewhere. But the glove was always left-handed. Its state was determined from the moment it was manufactured. With entangled quantum particles, their individual states aren't determined until the moment of measurement, and that measurement on one particle simultaneously influences the state of the other, regardless of distance. It's a correlation far stronger and stranger than anything classical physics allows. Entanglement is not just a curiosity, it's a fundamental resource for quantum computation and communication. It allows for non-classical correlations that can be exploited in algorithms. For example, it's essential for quantum teleportation, transferring quantum information, and for certain quantum algorithms that achieve speedups. Creating entanglement requires the systems to interact in some way. For atoms, this might involve bringing them very close together or using shared control fields to mediate an interaction between them. Unlike creating a simple superposition on a single qubit, entanglement always requires a specific interaction between the qubits. So far, we've explored the abstract weirdness of superposition and the interconnectedness of entanglement using systems, like electron spins and atoms, systems that are fundamental building blocks of nature. But how do we take these concepts and engineer them into a device we can actually program and compute with? This brings us to our third layer, the one that looks perhaps the most like a computer chip you might imagine: superconducting circuits. These intricate, beautiful chips you might have seen pictures of are currently at the forefront of quantum computing hardware. They are taking the principles we just discussed, superposition and entanglement, and implementing them in a completely engineered system. To understand how they work, we first need a little background on a special property of matter called superconductivity. Superconductors are a class of materials, typically metals cooled to very low temperatures, that exhibit zero electrical resistance. That means an electrical current, once started, can flow through a superconducting wire forever without losing any energy. Now, before you get too excited about infinite energy machines or perpetual motion, no, you can't use this to power your house for free. And yes, I'm absolutely sure. The energy still comes from creating the current in the first place, and these materials require constant cooling to incredibly low temperatures, often near absolute zero, which takes a significant amount of energy. But the reason for zero resistance is fundamentally quantum mechanical. Electrons are a type of particle called fermions, which have a rule. No two identical fermions can occupy the exact same quantum state. They like to stack up in different energy levels. However, under certain conditions, in a superconductor, electrons can pair up due to subtle interactions with the material's crystal lattice. These pairs, called Cooper pairs, named after Leon Cooper, who helped figure this out, behave like a different type of particle called bosons, and bosons love to be in the same quantum state. These Cooper pairs can all condense into the lowest possible energy state together and flow unimpeded through the material. This collective, coherent quantum state of millions of Cooper pairs is what enables the macroscopic phenomenon of zero resistance. Because superconductivity is rooted in this quantum behavior, the pairing of electrons and their condensation into discrete, quantized energy levels, The electrical circuits we build using superconducting materials also exhibit quantized energy levels, much like atoms do. For this reason, these superconducting circuits are often called artificial atoms. We can engineer specific circuit designs to create systems with energy level structures that look remarkably similar to the simple two-level systems we want for a qubit. A common way to build a superconducting qubit involves combining two basics, circuit elements, a capacitor and a special type of nonlinear inductor called a Josephson junction. Putting these together in a superconducting loop gives us a circuit with quantized energy levels. We can define the lowest energy level as our zero state and the next energy level up as our one state. Now, instead of using a laser to transition between energy levels like in an atom, we use electrical signals, specifically microwave or radio frequency pulses generated by control electronics. These pulses are sent down wires to the superconducting chip. The qubit circuit is designed to act like a tiny antenna, absorbing energy from the radio waves if the frequency of the waves precisely matches the energy difference between the 0 and 1 states. Just like the laser pulse duration controlled. The atomic qubit, the duration and amplitude of the microwave pulse, control the superconducting qubit. A microwave pulse with the right frequency and duration can flip the qubit from 0 to 1. This is our pi pulse, causing a 180-degree rotation on the Bloch sphere. And to put a superconducting qubit into a superposition, you guessed it, we apply a pi2 pulse, a microwave pulse at the correct frequency, but for half the duration of a pi pulse. This rotates the qubit state by 90 degrees on the Bloch sphere, creating a superposition of 0 and 1. And entanglement? Remember how with atoms, entanglement required the atoms to interact? With superconducting circuits, we create interaction by placing them physically close to each other on the chip and designing the circuitry such that they can mutually influence each other quantum mechanically. Applying carefully timed microwave pulses simultaneously to interacting qubits allows us to generate those special, spooky entangled states, like the Bell state we discussed. Superconducting qubits are exciting because they are highly controllable, using standard electrical engineering techniques, and potentially scalable using fabrication methods similar to those used for classical microprocessors. This allows for building chips with multiple interconnected qubits. This is taking the theoretical weirdness and physically engineering it onto a piece of silicon, or similar substrate, that sits in a very, very cold refrigerator. So there we have it. 3 examples: the lone electron, introducing us to the binary, potentiality of spin, and the strange blend of superposition visualized on the Bloch sphere. The atom, showing how discrete energy levels can be controlled with pinpoint accuracy using timed pulses of light, allowing us to create superpositions on demand, and the superconducting circuit, demonstrating how engineers can build artificial atoms using the quantum nature of materials controlled by radio waves to realize these quantum properties on a chip, enabling entanglement between multiple qubits simply by placing them next to each other. Each of these systems, in its own way, embodies the core ideas needed for quantum computation. Having well-defined, controllable quantum states, like Ariwo and Aliwalawanser, the ability to put them into superpositions, and the ability to entangle multiple states together. We started with Feynman's quote, suggesting that truly understanding quantum mechanics might be beyond us, and perhaps a full intuitive grasp of why it behaves this way, why measurement causes collapse, why entanglement exists, might forever remain elusive to our classical minds. But what these examples show us is that we don't necessarily need that intuitive grasp to use it. We've learned the rules of the quantum world, and we've figured out how to build systems that play by those rules. Quantum computing isn't magic. It's engineering. It's about building systems precise enough and cold enough and controlled enough to manipulate these incredibly subtle quantum states, harnessing superposition to explore vast computational spaces simultaneously, and leveraging entanglement to create non-classical correlations that power new types of algorithms. Thinking about this journey, from a tiny abstract electron to complex superconducting circuits, I've learned that understanding isn't always about seeing something clearly in your mind's eye. Sometimes it's about understanding the system's rules, how to interact with it, and what outcomes you can expect, even if the underlying why feels foreign. It's like learning to ride a bike. You don't fully understand the complex physics of balance and gyroscopic forces, but you learn the rules of interacting with the bike and the road, and you can ride effectively. This resonates with life, doesn't it? We often encounter situations, relationships, or problems that don't fit our familiar mental models. They feel messy, counterintuitive, maybe even weird. The lesson from quantum mechanics for me is to not be immediately discouraged if something doesn't make perfect intuitive sense. Instead, try to understand the operating principles, the rules of the system you're dealing with. How do the different parts interact? What inputs lead to what outcomes? By focusing on the mechanics, even if the fundamental reason remains a mystery, you can begin to work with it, control it, and maybe even turn its weirdness into a powerful tool for navigating challenges. Curiosity and a willingness to learn the unfamiliar rules can unlock new possibilities. If this exploration into the strange world of quantum systems and how we're making them practical sparked your curiosity, please give this video a like. What did you find most surprising or counterintuitive about these quantum systems? Let me know in the comments below. Do you think we'll ever have an intuitive grasp of quantum mechanics? I'd love to hear your thoughts. And if you want to see how these fascinating principles of superposition and entanglement are put to work to potentially revolutionize fields like medicine and materials science, be sure to check out this video right here, points to end screen card, where we dive into a groundbreaking quantum algorithm. Don't forget to subscribe to the channel and hit the notification bell so you don't miss our future explorations into the fascinating world of science and technology. Thank you so much for watching and joining me on this journey today. I truly appreciate you taking the time to explore these complex ideas with me. And as always, I wish you good health and keep exploring the mysteries of the universe.